Data consistency in the MySQL database system is provided by the locking mechanism that's implemented by the different storage engines. In the InnoDB storage engine, we are provided with row-level locks. And in the MyISAM storage engine, we're provided with table-level locks. The locks ensure that if one transaction is working with some row of data, that no other transaction can access that data while it is being changed by the first transaction. Recall also that a database is made up of tables. The tables are made up of rows. The rows are made up of columns. The columns contain the data. So when we talk about row level versus table level locks, we can support a higher level of concurrency, that is, multiple transactions accessing the same table at the same time when we use row-level locks rather than when we use table-level locks. So the row-level locks are significantly more efficient and provide a higher level of concurrency in the database. Typically, locks are managed by the database engine, by the storage engine itself. However, we as developers can take control of the locking during the execution of our transactions. This is not a good idea. In general, we should allow the locking mechanism to be managed by the storage engine. Now, since we're talking about locks, what happens when multiple transactions are competing for a set of locks within a table or a database? If transaction A is holding a lock and waiting for another lock, and transaction B is holding that other lock, waiting for the lock that transaction A is holding, then transaction A is waiting for transaction B, and transaction B is waiting for transaction A, and we have a situation referred to as a deadlock, where two transactions are waiting on each other to release resources. This is an amazingly common issue, and many of the occurrences of deadlocking can be traced back to poor programming practices. Now, how do we resolve deadlocks? Well, typically we don't resolve the deadlock. We try to program our SQL statements, our transactions, in a way that prevents or minimizes the occurrence of deadlocks. But once a deadlock occurs, the MySQL system has a process that runs within it to detect the deadlock. Once that deadlock is detected, the MySQL system makes a decision and terminates one of the transactions in the deadlock. How does it decide? Well, typically the easiest way to decide is to determine which of the transactions is the least expensive to roll back. So if transaction A has made fewer changes to the database than transaction B, then transaction A will be selected as the deadlock victim, rolled back, and terminated, thus freeing the deadlock and allowing transaction B to continue with its processing. Isolation in the MySQL system is provided by the isolation levels defined within the MySQL system, so that we can define how isolated transactions are from one another. There are 4 isolation levels provided by the MySQL system: serializable, repeatable read, read committed, and read uncommitted. These all have trade-offs. We need to understand what those trade-offs are so that when we decide which isolation level is appropriate for our application, we'll be making an informed decision. So these are the conditions that isolation helps prevent: phantom reads, non-repeatable reads, and dirty reads. And the chart defines how each isolation level responds to or provides protection from each of these three data issues that can occur when inappropriate isolation levels are used. Depending on your application, the isolation level will guarantee that if you run a transaction, that within that transaction you read a row of data twice for some reason, that within those two reads inside of that transaction, the data that you get returned will be the same, so that no other transaction or insert statement can change the values while your transaction is executing. This is the foundation of isolation within a database. So for durability, MySQL uses a binary log to record what the MySQL database system refers to as events within the database. An event is anything that occurs within the database that has an impact on the data. Binary log gets written to disk, and all transactions that occur on the database are recorded in that log, so that if there is a failure, the binary log can be used to recreate those transactions to put the database back in its correct state. Now, it's important to note that you are writing to the disk with the binary log. Therefore, that write operation uses resources, and that costs performance. However, to get the durability, the data safety, so that we can protect the state of the database, that performance cost is far outweighed by the benefits of binary log recording all transactions within the database. So let's go look at some code.